Okay, let's take a look at how we find pi on a desert isle. The humorous side of this is the desert isle, which is of course not entirely relevant to the problem, but the idea is how can we pick a random point repeatedly inside a unit square or inside a square and to determine pi doing this. And it turns out that this is a pretty common problem. So if you were to, inside Google, say finding pi in a circle with Monte Carlo, something like that. You go to images, you'll see lots and lots of images of people trying to show you what's going on here. And what's going on here is this. Say that we have right here a square, okay? And let's say that we'll actually take this portion of a square, the square where this point is 1, 1, and this point is 0, 0. Okay? So it's this square right here. And we pick a random point inside of here. And we do it over and over again. So we start filling it up as all these pictures are kind of showing you. Okay? Sometimes the point will be like point A and inside the circle. And sometimes it'll be like B and outside the circle. Of course, A and B are both always inside the square. So the question is, how many points in the end should we expect to be inside the circle? Well, if the circle had the area of half of the square, we'd expect half of them to be inside the circle. And in general, we'd expect it to be the ratio of the area of the circle to the area of the square. Now, if this point is 1, 1, the area of the square is simply 1 because it's a 1 by 1 square. Therefore, the ratio of the area of the circle to the area of the square is just the area of the circle. So what's the area of the circle with radius 1? Well, the entire circle, pi r squared, r is 1, so pi. The area of this circle is pi. So the area of this quadrant of that circle is pi over 4. So we expect pi over 4 of these points, or just over 3/4, to land inside the circle. So now what we do to find pi is we pick a whole bunch of random points. We find the fraction that occur inside the circle, and we simply set that equal to pi over 4. So we multiply by 4, and we have our guess for pi. That's that. So here's the code right here. Let's go ahead and copy this code. Pardon the fact that you can't briefly see it. Now you can. So here's the code. All right. So we're going to, and actually this particular version of it doesn't even do quite what I just said. I've implemented it different ways. Sometimes I just do the unit circle inside the unit, the quarter of the unit circle inside the unit square. In this case, we're going to go all the way from -1, -1 up to +1, +1. So it's this square. This square has sides of length 2, so an area of 4. The circle, now we're using the whole circle, so that's an area of pi. The ratio remains pi over 4, so it didn't change the problem at all, it turns out. You get 4 times as much area of the square and 4 times as much area of the circle. So we still do exactly what we said. We go in here and we find x and y, which are random floats between -1 and +1. And then if it's in the unit circle, that point, we increase our count to the number that we're inside the unit circle. When we're done, it's 4 times the number of throws that landed in the circle divided by the total number of throws. Have a couple helper functions here. We have random float and range and in unit circle. Random float and range, well, random.random is between 0 and 1. But we want to go between low and high. Say we wanted to go between, say, 20 and 80. Well, the first thing you do is you go between 0 and 60. And then you add 20 to that. So the 0 and 60 is because that's the total range involved. So what you do is you find the range that you need, and you multiply that by a number of 0 to 1, and this will give you a number between 0 and your range. And then you add that to the bottom. So again, if I'm doing between 20 and 80, this would be 60 times my random. This gives me a number from 0 to 60, to which I add 20, giving me a number from 20 to 80. In any case, this handy-dandy little function gives you a random float between low and high inclusive. Okay? So now, in unit circle. Oh, by the way, say low and high inclusive. Random.random, let's look up the notes on that. Python 3 random. And here we go. And you see random.random, which you'll find right here. Notice the parenthesis there. It actually never gives you 1.0, which means that this particular function will never actually give you high, although it can get arbitrarily close. Finally, in unit circle, a point is in the unit circle if x squared plus y squared is less than or equal to 1. And there you have it. Now what do? We will continue throwing with different numbers of throws. We'll have our throws increase exponentially. So we'll have 10 throws, then 100, 1,000, 10,000. We'll call find pi, which is this, with that number of throws. We've reviewed this. And then we'll go ahead and print out the result. So the result is just find pi. Oh, by the way, this should probably read pi guess. It's a little cleaner rather than calling it again. The accuracy is what? Well, what you do is you take the difference between our guess and actual pi, and then divide that by pi to see how close you are. Subtract 1 to turn it into if you were exact, this would turn out to 100%. And we go ahead and run this. As we see, when we only have 10 throws, we're actually pretty good. Even on 10 throws, 3.6. At 100 throws, 3.4. What's more interesting, I think, is the accuracy. So at 100 throws, we've got to 91, 92%. But as our number of throws goes up, our accuracy goes up. What's also interesting is it's non-monotonic. In other words, when we threw 10,000 throws, we are at 99.97, but at 100,000, 99.87, not as good. And at 1,000,000, only getting back to as good as our 10 to the fourth. I believe our 10 to the fourth was anomalous in this case. If I rerun this, you'll see, right, we do not see that effect in this case. So the reason is, well, this is partly to chance. And when you run it, there's every possibility, well, there's some possibility that weird things are going to happen, that even on 10,000 throws, you're going to get a number that's surprisingly far from your answer. However, the law of large numbers really does work. And the larger the number of throws, by and large, the greater the accuracy of our solution. And there you have it. We were able to find pi quite accurately by throwing coconuts into a circle.